I welcome you to today's ECD Star Introductory Colloquium on pertinent science topics of the workshop, Theoretical and Experimental Challenges for Flavour Hadrons, Heavy-Meson and Multiquark States, which deals with the spectroscopy of confined hadrons in the non-perturbative QCD. Experimental studies at facilities worldwide have produced a tremendous wealth of data in the meantime that have vastly improved our understanding of baryonic and mesonic spectra, in particular establishing the existence of new states in the chum sector. The nature of many of these states remains under debate, however, and the purpose of the workshop is to stimulate further discussions and new ideas for dedicated searches at existing and planned facilities, such as FAIR, NICA, the LHC, or JPark. The workshop was originally planned for 2020, but has been deferred to 2021 because of the COVID-19 pandemic. The intention of this workshop colloquium series is to introduce and publicize the science case of the workshop to a wider audience. Today's presentations will be shared between Mikhail Barabanov, the Joint Institute of Nuclear Research in Dubna, and El-Bennich from the City University of Sao Paulo. Let me briefly introduce the two speakers. Since 1998, Mikhail Barabanov has been working at the Wechsler-Baldin Laboratory of High Energy Physics at the Joint Institute of Nuclear Research and received his PhD in 2000 with a fellowship from the Bogolyubov Laboratory of Theoretical Physics in Dubna. Since 2010, he holds the position of a leading scientist at the Wechsler-Baldin Laboratory, which is similar to a professor position. His major interests are in particle and nuclear physics, especially in the structure of hadrons. He is an active member of the PANDA and NICA MD collaborations. Bruno El-Bennich received his PhD in 2004 from Rutgers University on antiproton annihilation into two mesons. From 2002 to 2007, he was a Marie Curie Fellow at the Sorbonne in Paris, followed by a postdoctoral position at Argonne National Laboratory from 2007 to 2009. From 2010 to 2014, he was assistant professor at Cruzeiro do Sol University in Sao Paulo, followed by an assistant professorship from 2014 to 2019 at the same place. At present, he's professor of physics at the City University of Sao Paulo, where he coordinates the master and PhD program. From 2021 onwards, he will move to the Federal University of Sao Paulo, where he intends to build a new hadron and nuclear physics theory group. He's a member of the Sao Paulo, Gießen, Bochum collaboration on PANDA fair physics and the Sao Paulo ANL collaboration on pattern distribution functions and the physics of the electron-ion collider. Thanks to both of you for your presentations.
Thank you. Dear colleagues, dear friends, good morning. Firstly, I would like to express my heart gratitude to the ACT staff, especially to Director of the Center, Professor Johann Wambach, and his assistants Susan and Mikhail for the fine and organization of workshops. So this colloquium is related to the workshop, which was scheduled at the early September of this year and was postponed because of well-known circumstances for the early autumn of next year. Colloquium is theoretical and experimental challenges in Flavour Hadrons, Quarkonia and Multiquark Physics. Besides the well-known facilities such as LHC, JPark, hadron colliders and electron-positron colliders. This research was related and was inspired and is related to two separate from one viewpoint and complementary to another viewpoint experiments. First of them is experiment with high-quality antiproton beams, planned and fair, so-called PANDA experiment. The program for this experiment covers a large program such as Flavour Hadrons, mesons and baryons with C and S quarks, charmonium and multiquark exotic states. Another experiment is based on nucleotron ion collider accelerator complex. Here you can find the brief sketch of this facility. Left part describes the existing facility with experiments and fixed target, and the right one part describes colliding ring, which is being built nowadays, and two detectors, multipurpose detector and spin physics detector. So in my contribution, I will briefly discuss physics case and motivation, conventional exotics hadrons, recent experimental review, and physics analysis and results. One of the great motivation initially was to look for different charmonium-like states in p-bar annihilation, proton-proton and proton-nuclear collisions to obtain complementary results to the ones obtained from electron-positron collisions, D-meson decays, and antiproton-proton annihilation process on a restricted scale of energy. Here you can find charmonium spectrum of charmonium-like states. The number of the particles is continuously from year to year increases. And now the quantity is about more than 30 particles, more than 30 states. Yellow and gray bricks are conventional states established and predicted, and red, purple, and green boxes indicate states which should have exotic nature, which should be good candidates for exotics. Green bricks shows candidates for the states with zero Charman strangers, red one neutral states, and purple charged states. The slide for botamonium-like exotics is slightly modest, but you can also find here as established one, as exotic one. Because of restricted time in my contribution in further discussions, I will pay attention at the charmonium-like states. Let us consider charmonium-like states. These states possess some well-favored characteristics. It is simple two-particle system consisting of quark-antiquark. It's compact bound state with small widths varying from several tenths of keV to several tenths of MeV, in comparison, for example, with light unflavored mesons and baryons. Charm quark has quite large mass in comparison to masses of UDS quarks. That makes plausible to attempt a description of dynamics properties of charmonium-like system in terms of non-relativistic potential models and also recently developed phenomenological models. Next one is quark motion velocities in charmonium-like systems. These velocities are non-relativistic, so coupling constant is not too large and the relativistic effects are manageable. And the next one, the size of charmonium-like systems is of the order of less than 1 Fm, so it's very small. So then one of the main doctrines of QCD, so-called asymptotic freedom, is emerging. Therefore, charmonium-like studies are promising for understanding the dynamics of quark interaction at small distances. Charmonium-like spectroscopy represents good testing tool for theories of strong interactions, and here means QCD in both perturbative and non-perturbative regimes, and QCD-inspired potential models and phenomenological models. This slide shows coupling strength between two quarks as function of their distance. For small distances, the strength is 0.1. It's region of light and flavor and hadrons, mesons and baryons. And theoretical description by perturbative QCD is applicable here. But for distances comparable to the size of nucleon, the strength becomes so large, so-called strong QCD, that quarks can be further separated. They remain confined within the nucleon, and another theoretical approach must be developed and applicable. Here you can find that coupling constant is 0.3 for charmonium-like states. Therefore, it's not small. One of such approach is quark potential models. These models have successfully described germanium-like spectrum, and generally potential contains three terms: linear, column, and spin-spin interaction. And more generally, it can also contain two more terms: spin orbital and tensor interactions. But the problem here is the following. These models give well description of observed states below the dB threshold. But there is not so good agreement between several experiments above the dB. Moreover, many of exotic states here, they marked by red color, don't fit into this scheme, into these models. Therefore, another approach or modification should be developed. One of such approaches or method was proposed some time ago. It's so-called combined approach based on potential model in combination with confinement model. In the core of the confinement model lays the fact that in the case of curved coordinate space with fixed radius and dimension, at the time dominant component of Glueballs potential, quark-antiquark potential defines via Gauss equation. And the physical system of decaying state, decaying resonance is compact. For example, three-dimensional sphere in four-dimensional Euclidean space, the harmonic potential assures the confinement. And for small distances, for small r parameter, which is equivalent to size of germanium-like state, we get again expansion suitable for column potential. Therefore, this approach together with quark models was applied to study the spectrum of germanium states above the dB and germanium-like states also, and the aim was to try to give this X, Y, Z states most obvious, most probable interpretation. The germanium system has been investigated in detail first in electron-positron reactions and afterwards on a restricted scale, but with high precision in proton-proton annihilation. That's experiments, for example, at CERN and Fermilab, but still the number of unsolved questions remains. For example, D-wave germanium states poorly studied. Little is known about partial widths of the states, higher lane singlet and triplet. PS-wave germanium states poorly investigated, and very little information about the partial widths of the states. So as a result, little is known on germanium states above the dB and many recently discovered states above the dB. Expect their verification and explanation. So the interpretation is far from being obvious nowadays. In general, one can identify four main classes of germanium decays, and the most important of them seems decays into particle-antiparticle, so-called open charm decays, and decays into light germanium plus light metals. For example, G psi, psi prime, HC plus combination of light metals. These channels were investigated by different groups, including our, and tend to quite good results, which should be checked experimentally. Besides conventional states, some non-standard hadrons should exist, and it doesn't contradict QCD principles. Moreover, evidence for QCD exotic states is a missing piece of knowledge about the nature of strong QCD. The number of the states is more than 10 nowadays, and most realistic seems pentaquarks, tetraquarks, meson molecules, and hybrids. I would like to remind here old paper by Gell-Mann and his co-authors. They also expected these states more than 50 years ago, theoretically predicted, but probably recently it opens a time and begins time for their revealing experimentally. Two different kinds of experiments are foreseen to study exotics: formation and production. If any states will absorb in production and not confirm information, it will be pure appointment for its exotic nature. Exotic germanium-like exotic hadrons tend to decay via hadron transitions and open charm final states, because namely these states possess significant branching ratios, fractions, and small widths. For example, decays into light germanium states together with light unflavored mesons are most interesting of the decays of these particles. This slide shows a summary of for candidates for exotic hadrons. As I told, the quantity is more than 30 now. And I would like here pay attention only for a few of them, pure exotic states, which have electric charge discovered by Bess some years ago. The results were obtained from experiments such as at initial stage at Bell and Baba, plus hadron experiments and hadron colliders, and afterwards from Bess and from LHCb experiments. The production mechanism of germanium-like states relevant to the X, Y, Z exotics are the following. Most of them only 4 mechanisms: B decays, gamma-gamma fusion, annihilation with initial state of radiation, and double germanium production. Here I would like to pay attention and briefly discuss only a few states which were discovered. First of them, which were discovered by Bess collaboration 6 or 7 years ago. These states probably represent isospin triplets. For example, first of them was discovered in GPSI pi-pi channel, and the state with close mass different for 5 or 10 MeV was discovered in open channel. As soon as we go up to the energies, new more heavy channels are opened, and next state, such as 4020, was discovered in HC pi-pi channel together with close with mass particle in D-star bar. So there arises a question: are the states the same, or it is different decay channels of the same states to be observed? Of course, to answer this question, other decay modes from also for scanning facilities will be very useful and will be very necessary to study this question. Are the states the same, or it is different? Another 4 states are LHCb new resonance, which were discovered in 2017, 3 years ago. First couple is the states were obtained as resonances in GPSI phi system. 2 of them contain quantum numbers 1++, which were confirmed by CDF and D0 hadron colliders, and next 2 states are the states with quantum numbers 0++, which were also confirmed by experiments with hadron colliders. In spite of no evidences in preliminary Kilke-Shudi studies for zero stranges and Cham tetraquark states, the existence of the states following from some other models, for example, from quark model and combined approach. Now I would like to discuss data which we obtained from the approaches and which need experimental confirmation. This slide shows spectrum of singlet and triplet germanium states. Black boxes correspond conventional states, white predicted states, and black-white the states which were predicted initially, but after can be interpreted as new discovered X, Y, Z states. For example, X3160 and 3940 can be considered as singlet states. Y states can be considered as vector states, and this is also coincide with methods with calculations made from quark models. For example, you can find the same states as scalar ready excited states. Similar picture can be shown for p-wave germanium states, and here also is some coincidence with quark models, so it's good. But of course, all this need to be experimentally checked and explained. And last slide with results which I would like to discuss. It's a quite new slide. Its structure is continuously modified because new and new states are discovered from year to year, from month to month maybe. It illustrates spectrum of tetraquark states. Here you can find that some states for example, charge states should have their neutral partners, and contrary, some neutral states should have their charge partners. For example, X3872, almost lowest exotic state, its quantum numbers was confirmed as 1 plus by LHCb 3 or 4 years ago. Expect its charge partner, and this falls from different model. And the contrary, the states which were discovered by Berin Baba expect their neutral partners. Also, approach doesn't distinguish the mass of the states with close mass discovered by Best collaboration. And here is some place for two states, X 4.5 and 4.7 map GeV, for states with hidden charm and hidden strangers. And here I would like to compare with with previous hypothesis or proposal made by Mayani, Pelosi, and Require 13 or 12 years ago. They also expect neutral partners of charge states Z4433. They also expected charge state with mass 3880 decaying into charmonium plus light mesons, and they also expected some states in the mass range 4.2, 4.3. Really, for example, these candidates, this state can be a real candidate for the states at range 4.2, 4.3, and these states good sample for 3880 expected many years ago. And here some more recent calculations proposed by Pelosi for the states with tetraquarks with hidden charm and strangers. He also expects that 4.5 and 4.7 0 plus resonances can be considered as radial excitations of the state with hidden charm and strangers. So some agreement with different models, different approaches is good. So next slide shows opportunity for calculation of width of the states. As we know, charmonium-like states should be narrow. They should not overlap. They doesn't overlap experimentally, and this is good chance, good opportunity to find them in experiment. Using integral formalism or so-called integral approach, this was applied many years ago for calculation of width of d Barabanov resonances, obtain us to results which are good agreement with experiment. For example, a brief piece of calculations for partial widths in comparison with experimental ones. You can find here good agreement between experiment and calculations. So this approach can be applied for calculation of widths of charmonium-like states. I would like to tell some words about experimental case. It's fine, I should repeat again that it's fine that we have some models, some approaches, but all the states should be confirmed experimentally. And moreover, it will be the best if they will be confirmed by different experiments, which are different. Here I would like to pay attention on physics with proton-proton and proton-nuclear collisions. Generally, the program is quite large, but one of the parts of this program is also study of Flavour Hadrons and mesons, hyperons, D-mesons, and also charmonium-like states and charmonium. As example, we checked how it's possible to select the events, for example, from proton-proton collisions at S² 25 GeV. The proposed luminosity was taken 1029 and 1030, and running time of accelerator, for example, 10 weeks. From this, we obtained that for 10 weeks, it could be selected, it may be selected about 3,000 events for chip size, so quite good expectation. Here you can find variant mass for A plus, A minus, and mu plus, mu minus distribution, so quite good signal for chip size can be absorbed here. It's of course inspire us for further researches in this physics. And what we have, for example, for firstly discovered exotic states, X3872, the similar calculations show that it needs 95 days at luminosity 1031 to obtain 1000 events, and to obtain 31,000 events we need 10 months at luminosity 1032. These estimations or calculations, of course, have preliminary character, and we now work on the further calculations and estimations. This slides shows reconstructed invariant mass of combination G psi pi pi in linear and logarithmic scale. After fitting the background, we find that signal can be well selected from the background. So this also inspires us for future research, for future studies. And in conclusion, I would like to tell some words about recently started project, small project, so-called probing of X and other meson structure with near-spatial PP, proton-proton and proton-nuclear collisions at the NICA facility. This project or proposal was offered by our group together with, in collaboration with Professor Stefan Olsen. He is our collaborator and co-author of several papers. Let us see how it can be done. How can the X3872 structure be proved? Good question. Following, as I told before, many of the states X, Y, Z have from few to several interpretations. So not one, many, several interpretations for all of the states. And from one of the most democratic interpretation proposed by Takizawa and Takeuchi, X represents mixture of three states. For example, tightly bound co-state CC bar with dimension more than 1 Fermi, more extended states D plus, D minus with dimension about around 1 Fermi, and most obvious, most special extended molecular state loosely bound with the dimension around 8 or more Fermi. The near-threshold experiments, production experiments with proton-proton collisions and proton-nuclear collisions with S squared starts from 8 GeV, when the NICA facility may be well suited to test the structure of X and possibly other exotic mesons. In these production experiments, X should be produced with relatively small kinetic energy. And because of interaction with nuclear medium of loosely bound molecular state, the survival probability of such molecule should be very small, and the production of X and probably other mesons should be strongly quenched. Thus, if this hybrid picture is correct, the atomic number dependence of X production at fixed energy should have dramatically different behavior than that of the case when it is considered as tightly bound charmonium state, charmonium core. So this method can give us opportunity, may give us opportunity to distinguish the states and obtain the nature of X and others. So in summary, I would like to say the following, that many of observed states, the problem is that many of observed states remain puzzling and can't be explained for many years. And this stimulates and motivates for new searches and ideas to obtain their nature. Exotics have been suggested by theorists since the onset of QCD. One encounters several new, interesting, difficult, and unsolved problems when modeling quark resonances. A combined approach based on the Quarkonia potential model and confinement model has been applied to study charmonium and tetraquark states. Together with quark model and tends to results which are in good agreement with experimentally observed states, especially laying above DD bar. Modern facilities with hadron and heavy ion collision should provide good opportunities for identification of charged and neutral particles. These experiments may shed light on the nature of X, Y, Z exotic states. PP bar annihilation experiments together with proton-proton and proton-nuclear collisions can obtain some valuable information on the charm production. And measurements of charmonium-like states may be considered as one of the pillars of PP bar proton-proton and proton-nuclear program. So thank you very much for the attention. And once again, I would like to repeat that all of you are invited and are welcomed for further fruitful collaboration and attend our workshop, which will take place next year at the ACT Star Trento, which should take place next year from 30th of August to till 3rd of September. In conclusion, I would like to thank you again and congratulate all of you with incoming Christmas, incoming New Year, and wish you all the best in future. Next part of colloquium will be continued by one of the organizers and one of the colleagues, Professor Bruno El-Bennich. Thank you. Goodbye.
Okay. This is the continuation of Mikhail's talk, who focused more on the experimental aspects of this workshop. So this is the workshop Theoretical and Experimental Challenges in Flavour Hadrons, Quarkonia and Multiquark Physics. A rather long title to put many aspects of hadrons with flavors. And it's going to be next year in September. Let me just remind the organizers, and if you look, there's 5 of them, and 4 of which are theorists. So for people who are interested in this workshop, I just want to remind, while only Mikhail is experimentalist, we really, in inviting the key speakers, aimed at having a balance between experimental and theoretical talks. So if you're interested as experimentalists, that's very important. Please do come. This is really about an exchange about several communities: flavor physics, hadron physics, heavy ion physics, anybody interested in heavy flavors. So I will probably repeat a couple of things that Mikhail already said, and I want to motivate from a theoretical point of view more what are our interests. And to do so, I will not randomly, but like start with a few 1-2 slides of general interest that motivates this workshop, and I just pick up some points, and later on I will develop them a little bit more. So from a theoretical point of view, what is important in flavor physics? Often in flavor physics, one thinks about, for instance, Heavy-Meson Decays, of course, heavy charmed hadrons, go beyond baryons, what are lambda C's and this, but in many cases, even people who look at flavor physics from a point of view of new physics, right, beyond some particle physicists, one of the problems that hinders some progress is actually hadronic effects that are not really well controlled. They stem from non-perturbative QCD contribution to strong weak decays. So this happens in beauty and charm decays, for instance. The hadronic, the strong phases, can significantly alter CP violating amplitudes in B and D decays, and their oscillations, or direct decays, and that precise knowledge is crucial for the work of experimentalists at LHCb and SuperCAP-B, so the HCB collaboration and BEL2 collaboration in Europe and in Japan. Charm decays, I want to point them out, and we'll come back to them several times, are particularly afflicted by the hadronic uncertainties since the corrections. Now, if you derive an effective Hamiltonian, have effective heavy quark theory, you have corrections of the order lambda QCD or MC, and they are not well under control. The charm sits somewhere in a very uncomfortable area between the light quarks and the B quarks, and it's not an easy mass range to control, theoretically. On the other side, you have also charmonium production. That's not really flavor physics with interest in CP violation, but in heavy ion physics. And it's sensitive to the existing properties of the intermediate quark gluon plasma, okay? And to final state directions, so J-psi decays that you produce charmonium. How do they interact with nuclear matter, with dense matter? How does this contribute to their suppression? Charm and beauty physics are obviously actively studied nowadays by the LHCb, BEL2, BEL3 collaboration, and so on. And Mikhail talked already about this. And in the future, PANDA, FAIR, and JLab will contribute further to the development of charm physics, and also NICA in terms of course, heavy ion physics and the phase spectrum. In this workshop, the theory conference will focus on non-partitive aspects of QCD. Okay, that's our main interest. So they can be based on several approaches: effective Lagrangians, NGL, for instance, models, or contact interactions model, simplified models of QCD, QCD sum rules, functional QCD approaches such as, for instance, Dyson-Schwinger equation or functional renormalization group, or basically working with continuum Green functions, Pidis-Alpeda and Valdiv equations to calculate bound states. Of course, lattice QCD, and also effective field theory based on meson degrees of freedom. Right? So all of them have their advantages, disadvantages, and current limitations. Right? And the current limitation, for instance, I know this area a bit better, of the functional approaches is often due to truncations, right? Because infinitely coupled integral equations, and at some point you have to truncate your kernels and you have to simplify. So many discussions will be about what is the current status, how far are we now beyond ladder approaches in mesons and baryons, or beyond baryons, for instance. What is the status of tetraquarks in this calculation? What about flavored mesons and heavy baryons? Similarly, what's the status of the mass spectrum decay constants, weak decay constants of Heavy-Meson and Quarkonia lattice approaches? How are they affected nowadays by volume effects, light quark masses? How do you extrapolate to the continuum limit? Many calculations are already relatively low pi masses. But so these are points we would like to discuss and clarify and compare between different approaches. Also very important are heavy light to transition form factors on the lattice. Particular case of heavy light mesons is very interesting and will be emphasized because it's a system, unlike Quarkonia, with very, very disparate scale problems. So you have soft collinear and hard scales. So the many ranges, and they can be factorized, but what then, right? You factorize your amplitude and write them neatly in some form factors, wave functions, and so on. But you still have to calculate them. Those are non-perturbative objects. For instance, light cone or light front distributions are not well known so far on the lattice. Only a few moments are available for instance, the K on the pine. And how do they compare, for instance, with the moments from other approaches? So these are basically some issues, some motivations, and things to be discussed in this workshop. And now maybe I will, I brought here selected topics. I can't possibly discuss them all, but I selected a couple of topics to illustrate what I just shortly summarized. So Hadron Spectroscopy, for instance, here I will repeat probably several things that Mikhail said, and I will go a little bit fast on this. Interesting, obviously for good reason, for a long time, historically, Glueballs, gluon excitations, right? And we do more a workshop about multiquarks. But beyond Glueballs, you also have hybrids. So valence quarks and antiquarks, plus one or more excited gluons, and they contribute to the overall quantum numbers. Those are very interesting objects. Harmonium spectroscopy, of course. Above open threshold, we have all the zoo, the whole families of the new XYZ states, some confirmed, some we don't know the quantum numbers now, and that will every year there are new states appearing and being measured. Also in D and F wave states, PANDA promises to measure masses with an accuracy of the order of 100 keV. D-meson spectroscopy beyond D-mesons, as often interested in, people are interested only in CP violation or in flavor physics or the CKM matrix elements. There's still a lot to learn about D-mesons beyond the ground state D-mesons, vector D-mesons, and the excited states. There are many new open charm states that are not found in the quark model. In particular, positive parity charm state mesons, the DS0 2317, DS1 2640. Can we find new ones? Can we explain them? Very important is the decay width, right? So the bandwidth is important when we extract them and compare with a model calculation to distinguish between the theoretical pictures. Are they still quark-antiquark mesons, or are there other objects? Are there molecular bound states, etc.? So I will come back to this a bit later. Baryon spectroscopy, improved baryon spectroscopy of multi-strange and possibly also multi-charm beauty mesons, right? So going beyond the hyperons and see what happens if you have, for instance, a CCU or other three-body bound states. Now, from a theoretical point of view, germanium and plutonium spectrum, this has been probably studied for already 2 decades or more now. Whether in quark models, functional approach, DSE, BSE, beta equation approaches, with that as considered, they are relatively well reproduced, the ground states. Now, the thing is a bit more tricky when you go to the radial excitations and exotic quantums. What's happening there? Several excited eta C, HC, chi-C states are predicted, but not experimentally found, for instance. Are these sort of results produced by the theory or by models that are spurious, you know? Shouldn't we take them seriously? So this is going to be discussed. For instance, in bit-star beta equation approaches, Quarkonia in the scale and action vectors are not well described in the interpretation due to continuing to see the approaches. So which corrections have to be implemented in this bit-star beta kernels? What is the status of Quarkonia and heavy baryons on the lattice? Those are all interesting questions. So what is the progress and which direction do we have to go? We will devote extensive time to from the experimental point and theoretical point to the germanium-like exotics and to spectra of neutron charged XYZ states. So are there quark? Should we work in a quark molecular picture, or are there hybrids? Are there maybe superposition of states? Effective theory approach versus quark model approaches? What can lattice tell us about them, etc. Beyond spectroscopy also, in the traditional sense, there are many predictions for charmed mesons and germanium interactions with nuclei. Can you form new bound state like germanic nuclei, for instance, where D-mesons bind for a short period in the nuclei? What is the status of hadrons at finite density and temperature, and how far are they, or how far are we from calculating bounds in mesoperiods under extreme conditions? Okay, so this is interesting in heavy ion collisions. What can we do, for instance, with D-meson at finite temperature in different approaches? So hadron spectroscopy, for instance, with PANDA, I'll take this as an example, has a great advantage that when you annihilate an antiproton or proton into some intermediate states, these intermediate states have quantum numbers like the proton-antiproton decay and all kinds of things. And the advantage over this production mechanism is that you're not limited, for instance, like in electron-positron annihilations into the vector or the 1 - states. You can observe all kinds of stirrings. PANDA promises resonant high statistics and extremely good precision, mass, and width. And so this is more or less here the range of mass range that PANDA will concentrate on and measure. And you see this overlaps with a broad area of all possible Glueballs, maybe tetraquarks, all possible Quarkonia. So many of them will be measured with much higher precision. This is just a little bit of a cartoon of what we have nowadays. So you have here, for instance, on the left, all the ground states of scalar and vector germania, right? And here, for instance, you have the J psi, you have the eta c. Here for L = 0, and here for L = 1 angular momentum, you have the HC, the chi's, and everything, and just here below the threshold. And what I haven't plotted here, or it's not plotted here, obviously all kind of radial excitations and other states, many other psi and etas that have been predicted by quark models. They're not here, but at least for this, we're pretty sure we know there are CC bar states like Quarkonia. Of course, there's whole zoo. The Z and the charged XYZ are missing here, the whole zoo of the new XYZ states. So the question is obviously, are these also quark-antiquark states, or these tetraquark states, where you could have a QQ bar and here in a bound into a colorless state, which QCD permits, or are they 4-quark states, but into, that interact via meson-meson interactions? So you have colorless mesons, but not a uniform coloriform hadron. Or are there maybe even superposition of these states? As I already said, glueballs are very interesting. We know that less of 2 or maybe 3–4% of the mass can be accounted for by the 3 valence quarks of the proton. Most of the proton mass is created by the strong interactions and we do the dynamical mass chiral symmetry breaking. So the gluon is important, its angular momentum, of course also the angular momentum of the quarks. But how exactly does all this happen? So glueballs are states where only gluons contribute the over quantum numbers and gain the mass solidly from the strong interaction. So it's a very nice testing ground for dynamical mass creation. The lattice calculation indicated the lightest glueball has a scalar, has the 0++ quantum numbers. But the problem is in these mass regions, you have many scalar mersons. So if you want to test, for instance, glueballs in final states, you'll have an overlap. This is not very clean in the analysis of the experiments. So hybrids consist of valence quarks and, as I said, an antiquark, so they can have 1 or more excited gluons as hybrids. And that's very interesting because it allows for JPC, for exotic quantum numbers. And the mixing with nearby bar states can be excluded, right? Because you know they have an additional gluon in there, and that makes experimental identification easier in the final state. So glueballs should be mainly produced in glue-rich environments. For instance, radiatives, you have Quarkonia decays, because of radiative decays of a photon. And then you have a bunch of gluons there, intermediate states, and this case in here in this picture only 2 mesons. This could be, of course, all kind of final states. As I shortly say, 3 mesons are very interesting. In central collisions, right? So central proton-proton collisions at certain energy in a certain RH, you also create this glue environment and produce final states. Or, for instance, as new facilities, for instance, in antiproton annihilation facilities, you will also create this glue intermediate state and observe the final states, mesonic final states. So the properties of glueballs and hybrids are defined by the long distance, and that's how you want to distinguish, right? Glueballs mix experimentally some scalar mesons. Hybrids have different long distance features. And if you study this, this will yield fundamental insights into the structure of the QCD vacuum too. The experimentally simplest way to look for scalar resonances is, for instance, or PANDA, for instance, will do it is at annihilation at rest into 3 pseudoscalars. And these 3 pseudoscalars, okay, so instead of having 2 here, you have through. Those are very interesting. This is work that goes back to the 60s. So you analyze this in terms of Dalitz plots. And you look basically at where most of the interaction between the final mesons takes place. Kinematic ranges, you see, for instance, here in this plot, there's not much happening in the center. And you see all kinds of scalar resonances, also tensor resonances. And then it's a work of serious experiments to work together through coupled channel approaches in effective field theory, through partial wave analysis, to reconstruct the states and see whether this was actually a hybrid before. Another topic is hadrons and matter. So this is also interesting for flavor physics, chiral symmetry breaking, partial restoration, extension of the medium modification to open hidden charm hadrons in hadronic matter, and this the in-medium mass of the states. So there's already quite a few theoretical predictions. I expect to be affected primarily by the gluon condensate. Okay, so in particular, there's a shape size. We know this. There's a lot of work about how the PANDA came, for instance, charge Finding there's a mass gap arising due to the effect of the nuclear medium and fine density. And how does this now you're going to go further on to the D-mesons and J-psi, because that's the mesons that are produced in the final states, for instance, of heavy ion collisions, so in matter-dense states. So if you compare the resonant J-psi yield obtained, for instance, from antiproton annihilation on protons and also nuclear targets, that allows you to use the J-psi nucleus dissociation cross-section. So knowing about the J-psi here in in nuclear targets tells you more the J psi, not only how they behave in vacuum. And this is a fundamental parameter to understand J psi suppression in relativistic heavy ion collisions, and can be interpreted as a signal for quark gluon plasma formation if you understand better how the suppression works. Okay, so you need to take these corrections, or you have to improve predictions for this. D-mesons, besides, as I said, the importance in weak decays and the accumulation, they play important roles in threshold dynamics of many of the so-called XYZ exotic hadrons. So how these XYZ mesons decay into D-mesons must be improved theoretically. And D-mesons in matter, they serve as a laboratory for studying chiral properties, right? Because it's not only pi, so you can study the light quarks UD not only bound into pi or in kaon, but also with a very heavy quark where you have very different scales, energy scales, and study them at finite temperature or in a density mu within different contexts will tell you more about the chiral properties of the light quarks. And for this, we need really make some improvements in theoretical approaches. I don't think I've seen that much yet. So how to D-meson interact with nuclei? So I said by annihilation, you have an antiproton in this range of 3.5 to 4.5 GeV. Collision, annihilation with the nuclei, you annihilate the proton. First, the total number of the nuclei is decreased by 1, and you produce some charmonia, okay? And the charmonia, of course, cannot be J psi, it has to be something at least above the DD bar threshold. The psi should be C, the Quarkonia CC bar state, then decays into a DD bar state, and the mesons interact with the nucleus at rest. In this, you have several possibilities. So here we have the psi 3770, which is basically the C bar and D quark, and the interaction proceeds. So the D-meson travels through this nuclear medium to the nuclei, and will interact with the protons there and the nucleons in general, right? So via the non-charm quarks, the light quarks, okay? And and this will be described in a meson exchange picture. What we ignore here, as I wrote there, is of course C or C bar nucleus interactions, which would probably be more complex. And probably the C would have to be closer to the protons and to the nucleons in general. You have other mechanisms like QCD van der Waals, so the Brodsky approach to QCD van der Waals interactions. This is here neglected. We see D-meson, and basically the things about DC bar or UC bars basically swimming through nuclei in interaction by, for instance, pi exchanges, etc. You could also have this here with a strain, for instance. You have quark nuclear interaction with a DS, so that would be kaon exchanges, and people, theorists, tackle this with effective Lagrangian approaches. So D-meson interaction with nuclei, for instance, I just show this a little bit differently. You have an antiproton and annihilates, for instance, with one of the protons. So this would be a very simple nuclei, just a deuteron. It annihilates, creates a threshold, of course, in between some Quarkonia, a DD bar, and the D bar rescatters, right, with one of the nucleons. And in effective Lagrangian approaches, this basically boils down to meson exchange models. You know, there's SU3, SU4 models. There's a lot of people, final state interaction, etc. So I'm not a specialist in this, but we hope that the people at the workshop will discuss these topics much more. Of course, these effective Lagrangians are not directly derived from QCD, so the couplings are not known, right? This is what I indicated with yellow dots. So how can people from other domains, fields, approaches help to basically improve these descriptions? I should also say that the nuclear interaction, there has been recent calculations also on the lattice that seem to hide that these states are not strongly bound state, or it's very difficult to form a bound state. Another very interesting application of charmonia is at the JLab and the Electron-lon collider. So spatial imaging of gluon and nucleus center in a nucleon or nucleus. So that goes back to work of Brodsky and colleagues, like exclusive photo production. So the way you produce, for instance, you do photo production of a pi or kaon, you could do this also with Quarkonia, right, of J psi. what goes here. Here's the in the first simplest approximation, the Handbuck diagram. And you have a t-dependence. Is just the difference between the final and the initial momentum. Okay, the momentum transfer. And if you take the Furthermans of the t-dependence of this scattering amplitude, you can actually learn something about and so they have a prediction of you look at the scattering cross section. From this, you can actually probe the energy momentum tensor of the proton and can yield a unique probe of the spatial imaging of this glue density. You can extract actually information on this energy momentum tensor indirectly. And in this case, this is different, as I mentioned before. Here we consider actually in this exclusive production, we consider actually the Quarkonia interaction by exchanging gluons with nucleons like quarks. So these are different forces, not meson interaction. So this is a very, very interesting and promising approaches to learn more about basically what creates the mass or produces the mass of the proton, and what in particular is the percentage, exact percentage of the gluon contribution. So let me probably finish with what Flavour Hadrons are the most famous for, flavor physics in general. So for the last 2 or 3 decades, D and B-mesons have been studied, and I mean, the main object study of flavor is the origin of CP violating phases. This goes back to cosmology, the origin of the universe, and in weak decays, how parity is violated, CP violation, etc. So I think by now we could fairly say that the Cabibbo, Kobayashi, and Escava mechanism has been established as a dominant standard most source of CPM violation. That doesn't mean there could be other sources of CP violation, other weak and strong phases from, and a lot of the work of particle physics concentrates on contribution from new physics. But the point is here that in these decays, a lot of the strong phases are not very well determined, and they interfere with the weak phases. Okay, without strong phases, you can't have any CP violation. The amplitude needs at least 2 Feynman diagrams, for instance, to proceed for. And in this relative phase, strong phase is needed, so you can actually have CP violation. Now, consider, for instance, a Heavy-Meson decay. Just random, I took here B-meson. It decays into, it's a non-leptonic decays in 2 final mesons. That could be 2 pions, kaons, rows, doesn't matter. We have here effective 4 quark operations, like in the Fermi theory, that effective in a certain sense that these 4 quark operators and non-local operators are obtained from a heavy quark expansions, right? As I said already, this is a little bit tricky when you look at D-mesons, because lambda QCD over MC corrections are not well controlled at all. And a lot of work in the past, say, 20 years has been on factorization approaches. So going beyond factorization approaches from proton and light mesons to heavy mesons. And this amplitude can be, this schematic I wrote here, factorized in a weak decay amplitude, right? So from vacuum, you create a meson by a weak current. At transition form factors, this would be if you just, in the simple naive factorization stop here, you can show that you, in some cases, not all, that you can systematically sum over radiative corrections that occur in this decays, and you have corrections that come from expanding the operator in a heavy quark effective theory. So the weak decays constant, this will be a topic. The latest people at this workshop will fill us in, and also people from BC approaches and other approaches will fill us in on what's the status of decay constants, for instance, the B, BS, D, DS, and other mesons, also Quarkonia, pi and kaon, of course, are known experimentally. More delicate and more complicated hadronic transition form factors. So by a weak current, you have a heavy meson that becomes a light meson, and I've sketched this here, and basically all kind of things can happen. You have your B or a D meson, it decays here via a W boson, and of course you could have all kind of corrections to this. So how do you compute this? What is the status here? There have been estimated QCD sum rules, status QCD, quark model calculations, Schwinger, Peter approaches, etc. So what effective field theory mostly did in the last 2 decades is impressive work on factorizing the scales in this. As I said, the heavy light mesons are very interesting, but that makes them also very complicated. Is that unlike Quarkonia, or for instance, the pion, you have a very heavy scale, light scale. So you're here at the weak interaction. You have the hard scales. You have soft scales here in the final states. You have soft collinear first scales here, somewhere in the middle and the transition. And you can factorize them in different parts of the amplitudes. And that's all nice. And you can then systematically account for corrections here at the hard scale in alpha S, and possibly look at corrections in lambda over the heavy quark mass. But at the end, you end up with wave functions, transition form factors. All this still needs to be calculated. So that's very interesting from the point of view of a hadron physicist, theorist. I'll just mention here some recent work, for instance, from the lattice. This is on D to Pine transition form factors, D to K2. I don't now really, this is D to Pine. And so you have the scalar form factor. So for instance, from pseudoscalar to pseudoscalar transition form factors, you have 2 form factors. You can write them as an F0 and F plus. The ISTI collaboration has done this for primers that are down to 210 eV. That's not the film. Then they do extrapolations to the physical pi mass and continuum infinite volume limits. Those are these bands, okay, for the 2 different form factors. They've done this for several ensembles, different D-meson masses, and also with much more precision. And also there are some also include a lot of kinematic constellations. So for instance, D-meson at rest and different kinetic energies. So this is quite some impressive work. And so the past decades, 2 decades, there have been strong improvements from several collaborations in Japan, Europe, US, on these form factors. And there's still some disagreement with experiment at larger Q squared. So the interesting, though, this extrapolated result, how are these discretization effects and final volume effects? I haven't plotted here. There are also figures, recent work on this from Dyson-Jr. and Bizarre Beta approaches and quark models. How does he compare this? What are the errors, the error budget in these approaches? What are the simplifications? Improvements in B to pi transitions. These are more complicated. Of course, you have a much larger kinematic phase space here. But this is still done with rather large pi masses, and there's some recent work, the Japan lattice QCD collaboration. Other important inputs, non-productive input that's interesting for flavor physics is in this case, in this factorization. You can write this, for instance, in this form. You could write these amplitudes as a convolution of a hard scattering kernel, right? That depends on the quark masses, momentum fractions, and the momentum fractions corresponds to the mesons that are here actually acting. So there would be the Heavy-Mesons, the 2, for instance, in this case, to charge light pions. You integrate of this hard scattering kernel. There are a lot of calculations nowadays that go beyond leading order in PQCD. Those objects, are non-perturbative. So these are basically, think of them as your wave function of the mesons on the light front. And you can expand them basically in Gegenbauer polynomials. The asymptotic one, as you know from Brodsky words, is simply x1 minus x. And what you can do actually with this exponentials, you can calculate Gegenbauer moments, and this whole exponent, basically this whole expansions were pretty known until not very recently. These LCDs have been now determined for them. 2 Gegenbauer moments have been determined for the pi and the kaon. That's actually has been shown to be sufficient already to reproduce the LCDs to some extent, but they have been calculated with higher precision compared to other approaches. And this is what is known for now. So what are the next steps? This is from the Regenburg collaboration in Germany. Next to nothing was known about heavy light mesons recently. So mostly models or asymptotic LCD, or people used whatever they could find. And the recent results using these EBC calculations, projecting the light front, this is our group here in Sao Paulo, have worked on this, and so there have been not only have been many moments calculated for the etas. So we've done this for pseudoscalars, the etas, eta C, eta B, D-mesons, B-mesons. As you can see, distribution, so a large range of moments have been calculated, and you can reconstruct from them. You can reconstruct this distribution from a few moments, but of course there's a large error involved. So you can see that, of course, the distribution values for the eta C and eta B are very central. Obviously, those are symmetric mesons. Each of the quark and antiquark carries the same amount momentum fraction of the mesons total momentum. And if you go, for instance, to the D-mesons here, right? So the gray one, this peak here, and is more and more, and also for the DU and for the DS, are shifted to the right. That means the heavier quark carries more of the momentum, and this is, of course, even more so in case of B-mesons, where the asymmetry inside the momentum distribution asymmetry within the B-meson is much larger than, for instance, in kaons and in charmonium. In charm mesons, for instance, D-mesons. Okay, with this, I want to conclude. This was supposed to be a little bit of summary of the topics that are interesting from a theoretical point of view, the different approaches, now without showing any equations or anything that will be applied to these problems, and we want to discuss in this workshop. So to summarize, Flavour Hadrons, the Flavour mesons of heavy Quarkonia, they're interesting by themselves, right? Independent of in where they play a role in heavy ion collisions, CP violations, because they allow for different insights on perturbative, non-perturbative aspects of QCD, right? This is complementarity, what we know to light meson phenology, what we know from about QCD from nucleon physics, form factors, etc. The spectrum, especially that of exotic, and multiquark states and other properties are important to establish furthermore that QCD is a theory of strong interaction. We believe this, but obviously, if QCD is a real theory of strong interaction, it has to also reproduce all these states. Okay, and so this works hand in hand between experiment and theory, which all the complications, because many of the states are not that easy. They're not pure and simple QQ bar state or 3-quark states, and even if they're only in their tetraquark states, there can be, of course, hybrids, and there could be, for instance, superpositions with molecular states. So that's not a trivial task. Beyond the mass spectrum, charm and beauty mesons are also interesting. Nice laboratory to study bound states with statistically separate energy scales. So this is another bonus in QCD. And for instance, you can study the chiral properties of the light quark in these bound states at medium final temperatures. It's important for charm suppression, heavy ion collision, for instance. So as we saw, for instance, interaction of D-mesons with nuclear matter is very important. The interactions of charmonium with protonucleon, as I tell you, this is the physics of EIC, can tell us much about the gluon contribution to the dynamically generated hadron masses, right? So what gives, we know that the Higgs mechanism gives very little contribution to the hadron masses, at least to those formed out of U and D quarks. So this will be very interesting. And heavy mesons have been studied for decades now. That's clear. The various accelerators, we had Bell, we had, of course, now we have LHCb, we had Barber in the past. On those, they produce a huge amount of data and very exciting results up to the recent, for instance, CP violation, DD bar oscillations. And this is to determine, of course, with most precision, the CKM matrix elements. So physics beyond standard models is important, and that motivates experimenters, but a lot from this LHCb physics for currently and Bell 2 actually amounts to learning about QCD 2. And with this, I want to thank you and close this talk.